In this section, we're going to learn about something called the common ion effect and buffers. A solution that is made up of a weak acid and its conjugate base will have a different pH than that of just a pure weak acid. In your notes, we previously calculated the pH of a pure 0.1 molar acetic acid solution, and we figured out that when we did our dissociation of a weak acid problem, that the pH came out to being about 2.88. Now what we're going to imagine is if we make a solution up and we have some acetic acid in it and we mix in something like sodium acetate, where the acetate would be a common ion to the acetic acid. So we'll imagine we mix 0.1 moles of acetic acid with 0.1 moles of sodium acetate and we dilute it up to 1 liter. What would be the pH of this new solution that contains a common ion? Calculate the pH of a 0.1 molar acetic acid solution that has been made 0.1 molar in sodium acetate. So what this means is we have our weak acid dissociation that we can write. So acetic acid, we know will dissociate into hydrogen ion and acetate anion, C2H3O2-. According to Le Chatelier's principle, if we were to make it up in sodium acetate, the sodium is essentially just a spectator ion, and we see the acetate anion in our original equilibrium expression for the dissociation of our weak acid. So we can imagine that if we were to spike it with acetate anion, we would shift away from the addition of the acetate towards the acetic acid. So we would shift to the left. We want to see how that's going to impact the pH of our solution compared to just a pure 0.1 molar acetic acid solution, which we said the pH of that pure acetic acid solution that we calculated previously was about 2.88. So we're going to start off by making an ice table because we still have a weak acid solution. Our initial concentration of our acetic acid, we can plug in here into I line, 0.1 molar. And initially, we assume no dissociation of our weak acid has occurred. So normally we come over here and we plug in 0 for hydrogen ion, and we also normally plug in 0 for acetate. But this time, we have a common ion. The solution has been made in 0.1 molar sodium acetate. So we're actually going to plug in 0.1 molar for our acetate anion because we do have some from the sodium acetate that it was made in. This is where that common ion comes in. Next, we want to decide what we're going to call our X, and we usually call X the change in the amount of the acid that dissociates or ionizes. So this would be minus X, the hydrogen ion would be plus X, and the acetate anion would also be plus X because everything in our balanced equation has a stoichiometry of 1 to 1 to 1. And our equilibrium line will be 0.1 minus X. It'll be X for the hydrogen ion, and it'll be 0.1 plus X for the acetate anion. Next, we want to write our equilibrium expression. Ka will be equal to the hydrogen ion concentration times the acetate anion concentration divided by the concentration of acetic acid. And when we substitute in, we're going to use our equilibrium line and plug those values into our equilibrium expression. You can use your Ka-Kb chart to look up the acid ionization constant for acetic acid. The Ka for acetic acid should be 1.8 times 10 to the negative fifth. Now remember, usually the Kas and the Kbs for these weak acids and weak bases are going to be small. Because they're small, we're usually going to be able to make some simplifying assumptions regarding X's that are added or subtracted. So 1.8 times 10 to the minus fifth, we'll plug that in for our Ka. Our hydrogen ion was X. Our acetate anion was 0.1 plus X, and our acetic acid was 0.1 minus X. Because our Ka is so small, we can ignore our plus X in the numerator and we can ignore our minus x in the denominator. So what our equilibrium expression simplifies down to is the Ka, 1.8 times 10 to the minus fifth, is equal to x for the hydrogen ion times 0.1 for the acetate anion over 0.1 for our weak acid concentration. And because in this problem, the concentration of our weak acid and its common ion were the same, those two are essentially going to cancel, and x will end up equaling the Ka. So x will equal 1.8 times 10 to the negative fifth, which x was, according to our ICE table, equal to our hydrogen ion concentration. So now to get the pH of our solution, that will be equal to the negative log of the hydrogen ion concentration. We'll take negative log of essentially our Ka, negative log of 1.8 times 10 to the minus fifth. And that gives us a pH of about 4.74. So when we had just a 0.1 molar acetic acid solution in a previous problem, our pH was equal to about 2.88. And when we made up a weak acid solution with a common ion, sodium acetate, our pH jumped up to 4.74. So the pH is greater in a common ion solution than it is in just a pure weak acid solution. Essentially, the presence of that acetate anion in solution made our pH a little more basic. And having a weak acid in solution with some of its conjugate base is actually called a buffer solution. Let's try another common ion example. In a pure 0.15 molar ammonia solution, the pH is 11.21. Calculate the pH in a solution that is 0.15 molar ammonia and 0.45 molar ammonium chloride. How do the values compare to that of the pure ammonia solution? So NH3, or ammonia, is a weak base. And if we were to go through and do a problem where we just calculate the pH of that pure weak base, we would get about 11.21. So now we want to see how that will change when we have a common ion, and the common ion is going to come from the ammonium chloride. The chloride is essentially a spectator ion, and NH4 plus, or ammonium, will be our common ion source. So if we write the initial dissociation of our weak base, we would have NH3 plus H2O, and our weak base would accept a proton from water, forming NH4 plus ammonium, and our water would be hydroxide ion when it loses a proton. So if we think about what's going to happen, we're spiking our weak base solution with extra ammonium ion from the ammonium chloride. So according to Le Chatelier, we should shift away from that addition. So we should shift back in this direction towards the left, which is our ammonia and our water, and shifting away from our hydroxide ion. So how will that affect the pH? We can set up our ICE table. Initially, our concentration of NH3, we were told, is 0.15 molar. Remember, you can ignore the water because that's a pure liquid. Initially, from just the dissociation of our weak base, we normally would have 0 ammonium ion and 0 hydroxide. We're still going to have 0 hydroxide from the dissociation, but this time we're going to actually have a little bit of ammonium ion in there from our common ion. So we're going to have 0.45 molar ammonium ion in our solution. Dissociation of our weak base, we would say the change is going to go down by minus x. For the ammonium, it'll be plus x, and for the hydroxide, it'll be plus x. Our equilibrium line will be 0.15 minus x for ammonia. It'll be 0.45 plus x for ammonium, and it'll be just x for hydroxide. Next, we want to write our equilibrium expression. This time we're going to use K sub B because we're dealing with a weak base, not a weak acid. We're going to have K sub B is equal to the concentration of ammonium ion times the concentration of hydroxide ion over the concentration of our weak base, ammonia. We can look up the Kb for ammonia off of our acid-base ionization chart. The Kb for ammonia is 1.8 times 10 to the negative fifth. So we're going to plug that in and also plug in everything from our equilibrium line. 1.8 times 10 to the minus fifth is equal to, we're going to have 0.45 plus x for NH4 plus. We're going to have x for our hydroxide ion all over 0.15 minus x for our ammonia concentration at equilibrium. And once again, our Kb is a relatively small value, so that means we can ignore our x's that are added or subtracted. So we can ignore this plus x in the numerator, and we can ignore that minus x in the denominator to help simplify our algebra. That means our equilibrium expression will reduce down to the Kb, 1.8 times 10 to the minus fifth, equal to 0.45 times x in the numerator, all over 0.15 in the denominator. So we can multiply both sides by 0.15, and that gives us 2.7 times 10 to the negative sixth is equal to 0.45x. And then we'll divide both sides by 0.45 to get x. So x comes out to being 6.0 times 10 to the negative sixth power. And that value is equal to our hydroxide ion concentration. So that's our OH minus. To get the pH, first we should calculate the pOH by taking the negative log of our hydroxide ion concentration. So we'll have a negative log of 6.0 times 10 to the negative sixth, and that gives us a pOH equal to about 5.22. Now to calculate our pH, we're going to want to use the pKw, which is 14, minus the pOH of the solution. So our pH will equal 14 minus 5.22, giving us a pH of about 8.78. We got a pH that was greater than 7 because it was a basic solution. But how does that compare to our pH of our solution of just the weak acid that did not contain a common ion? So the pH of just a pure 0.15 molar ammonia solution was 11.21. When we took the pH of that ammonia solution that had ammonium chloride in it, or a common ion, now the pH is less basic. It's a little bit more acidic because we shifted to the left. We shifted away from our hydroxide ion towards the ammonia and the water. So it makes sense that it was less basic or more acidic than just the pure ammonia solution. The last two common ion examples that we went through were actually examples of buffer solutions. Buffers are solutions of a weak acid with its conjugate base. They resist drastic changes in pH. So you can add strong acid or strong base to a buffer solution and the pH won't actually change very much, even though you're adding a strong acid or a strong base to it. When you add a small amount of acid or base, the pH will not change because some of it will end up being neutralized by either the weak acid or the conjugate base in there with it. An example of a buffer system you may have heard about before is called the bicarbonate buffer system. And your blood is a buffer that contains carbonic acid, which is H2CO3, and the bicarbonate ion, HCO3-. It helps your blood maintain a pH of about 7.4. If your blood pH deviates too much from that 7.4, you can either enter acidosis by going lower on the pH scale, or alkalosis if you go a little bit higher on the pH scale. So once you're out of this 6.8 to about 7.8 pH range for your blood, you can actually die because you've deviated too far. That's why we have this buffer system in place to help absorb any additional acid or base to avoid the pH becoming too high or too low. We previously did a common ion problem where we had a solution of acetic acid that was made up in sodium acetate. Both of them were 0.1 molar. we could think about how this buffer system of acetic acid and sodium acetate would react if we added strong acid, any strong acid really, so we can just say H3O plus for short, or any strong base, so we can say hydroxide ion for short. We calculated the pH of our buffer system, and initially it was 4.74. Now the pH can deviate from 4.74 if we add strong acid or strong base. If we add acid, it will go a little bit less than 4.74. If we add base, it'll go a little bit higher than 4.74, but it should maintain a relatively constant pH. It won't change drastically because it is a buffering system. So we have our overall equation for the dissociation of our weak acid. Maybe we can rewrite this: HC2H3O2 plus H2O, and that's in equilibrium with the hydronium ion and the acetate anion, C2H3O2 minus. The way it's written below is just a little bit different way of expressing the formulas for acetic acid and acetate anion. So how will this buffer system adjust essentially if we were to add in some strong acid? If we were to put in any strong acid, we're essentially really adding hydronium ion. So we're adding in extra H3O plus. So according to Le Chatelier, when we add in extra hydronium ion, it's going to want to use up that extra hydronium ion and shift away from that addition. So the addition of the strong acid will cause the equilibria to shift to the left, and it will react away that hydronium ion by reacting with any additional acetate anion lying around, forming more acetic acid. So what we will see after we add H3O plus is that you'll end up with a greater amount of acetic acid and a lesser amount of acetate anion. Now, if we were to think about how our buffer system will react if we add a strong base, such as hydroxide ion, the hydroxide ion will actually react with the acetic acid in the solution. If it reacts with the acetic acid in the solution, it will come along and it will remove a proton from the acetic acid and will form water and will form more acetate anion. So it'll end up shifting the position of equilibrium to the right by forming a greater amount of acetate anion, and we'll end up with a little bit lesser amount of acetic acid. So after the addition of a strong base, we have a higher amount of acetate, and we have a lesser amount of acetic acid. So whenever we're approaching a buffer problem, we want to think about, are we adding a strong acid or a strong base? And how is the position of equilibrium going to be affected by that strong acid or strong base? In these next examples, we're going to look at the buffering system a little more in depth and figure out how we can actually calculate the pH of a solution after we add either strong base or strong acid to the buffer system. So initially we did a common ion problem where we had 0.1 molar acetic acid made up in 0.1 molar sodium acetate, and the pH of that buffer system was 4.74. Now we want to think about what's going to happen to the pH of that solution if we add in 0.01 moles of sodium hydroxide, which is essentially adding a strong base. And how would our buffer system react? We're also going to make the assumption that there's no volume change that's occurred when we add in that 0.01 moles of the sodium hydroxide. So initially we want to write the dissociation of our weak acid. So we have HC2H3O2 in equilibrium with H plus and C2H3O2 minus. And remember, that's kind of the shorthand notation of writing the dissociation of the weak acid, where we have H plus instead of H3O plus. However you like to write that, it'll work out the same. So imagine that we have a flask containing some of our buffer solution. So we've got about 0.1 molar of acetic acid, and we've got about 0.1 molar of acetate anion. What is going to happen if we start adding in a couple drops essentially of hydroxide ion into our flask? So our hydroxide ion, we're adding it in, drop, drop, drop. That OH minus is going to come and rip a proton off of our weak acid. It's going to react with that weak acid. So the hydroxide ion reacts with our acetic acid in the buffer system, causing there to be less acetic acid. So however much hydroxide ion we add in is going to cause the amount of the acetic acid to go down by that amount. So it's going to decrease. And what our reaction occurring there would be is we would have hydroxide ion plus acetic acid, so plus HC2H3O2, forming H2O plus C2H3O2 minus. So this is just kind of that side reaction that's occurring when we add some drops of hydroxide or a strong base in. Notice that however much the acetic acid goes down by, so however much that proton gets ripped off, every drop forms some acetate anion. So the concentration of the acetic acid will go down, but the concentration of the acetate anion will go up by that same amount that we add the hydroxide ion in. So when you add a strong base, this is how the buffer system will react. The weak acid amount will go down, the conjugate base will go up because it'll be formed when that proton gets ripped from the weak acid by the strong base. So our overall reaction we're going to use will be the first one we wrote, which is the dissociation of our weak acid, while this second one is just kind of that side reaction that's taking place from adding in some of that strong base to our overall weak acid solution. So recall that we could write our ice table, but it would reduce down to our equilibrium expression being the concentration of the hydrogen ion times the concentration of the acetate anion, all over the concentration of our weak acid, which is acetic acid in this case. And I'm looking at our initial dissociation of our weak acid reaction. And we would have looked up the Ka for acetic acid, which if you look at your acid-base ionization chart, you'll see it's 1.8 times 10 to the negative fifth. And then we would have plugged in our concentrations. And we had some simplifying assumptions we could make. Hydrogen ended up being X. The acetate concentration was 0.1 initially, and it would have been 0.1 plus X, but we ended up ignoring that plus X. And the acetic acid would have been 0.1 minus X, but we also ended up ignoring that X. So it kind of reduced down to something like this in that previous problem that we did. Now, we have to account for the fact that we have that buffer system, but we're adding in 0.1 moles of our sodium hydroxide. So we're going to have to adjust what we plug in for our acetate and our acetic acid by how much base we added. So we're going to take our initial concentration of our acetic acid and we're going to subtract it by how much base we added because it's going to go down by that amount. And we're going to take our initial concentration of our acetate and we're going to add how much sodium hydroxide we added because it's going to go up by that amount. So our buffer system, when we add strong base to it, will end up changing and being, we'll have X for our hydrogen ion concentration. For our acetate, that's going to be 0.1 plus however much base we added. We added 0.01 moles of base. So since we're assuming no volume change, we'll just simply add 0.01 to that value because that went up by that amount, over our weak acid concentration, which was 0.1 for our acetic acid, but that's going to go down by a certain amount. It's going to go down by how much base we added, so we're going to subtract 0.01. And so this ends up reducing down to, we can say 1.8 times 10 to the minus fifth is the Ka. We're going to have X times, on the top we'll have 0.11, and on the bottom we'll have 0.09. And we can solve for X. We can multiply both sides of the equation by 0.09. So we'll have 1.8 times 10 to the minus fifth times 0.09. And that will give us 1.62 times 10 to the negative sixth. And that will be equal to 0.11 times X. And then we'll divide both sides of the equation by 0.11. And that will give us X is equal to 1.47 times 10 to the negative fifth. And in this equilibrium, because we had a weak acid, we're going to have X equal to our hydrogen ion concentration according to our ice table. And so finally, the question was, what was the pH after we added that strong base, that sodium hydroxide? We'll take the negative log of our hydrogen ion concentration. So negative log of 1.47 times 10 to the negative fifth. And that gives us a pH of about 4.83. Now, initially our pH of just the pure buffer system was 4.74. We got that by doing that common ion problem. And notice that our pH did increase a little bit. 4.8 is greater than 4.7. We added a strong base, so it did get slightly more basic, but it didn't increase very much. If you were to add a strong base to a non-buffered system, the pH would jump all the way up to 11 or 12, something very, very basic. But because this buffer system was able to essentially neutralize some of the strong base by reacting it with the acid portion, the pH did not increase very much. So we only had a slight increase in our pH. Now let's do a similar analysis by adding a strong acid to our sodium acetate acetic acid buffer system. So we can still start by writing the dissociation of our weak acid HC2H3O2, dissociating into H plus and C2H3O2 minus. We start off with some amount of our weak acid, 0.1 molar, some amount of our conjugate base, 0.1 molar there. We imagine that we've got both of those in a flask together, and now we want to see what happens when we add 0.01 moles of HCl. HCl or just any strong acid, the same thing would occur with any strong acid that we're adding. So really the important part of adding a strong acid in is we're dropping in essentially a bit of hydrogen ion with a strong acid. We're dropping in some H plus. And in this case, the hydrogen ion, when you add it in, that will go and react with the conjugate base in the solution. It'll react with that part of the buffer system. So the hydrogen ion would combine with the acetate anion. That's going to cause the acetate anion to go down by the amount that you add the hydrogen ion in. And so this side reaction that would occur would be the combination of our hydrogen ion plus our acetate anion forming some acetic acid, HC2H3O2. So however much acid you add, that's how much our acetate will go down by, and the same amount our acetic acid will go up by. So strong acid reacts with the conjugate base portion of your buffer system. So we can write our equilibrium expression. Ka was equal to H plus times C2H3O2 minus all over HC2H3O2, our weak acid. But in this case, we want to look at how we're going to have to add or subtract. We're going to have to subtract from the acetate concentration, and we're going to have to add to the weak acid, the acetic acid portion of it. So we had 0.1 molar acetic acid and 0.1 molar acetate, and our Ka is going to be the same because we're still dealing with acetic acid, so 1.8 times 10 to the negative fifth. We can plug that in for our Ka, and it's a small value. So originally we had that simplifying assumption where we had X for our hydrogen ion, we had 0.1 for our acetate, and we had 0.1 for our acetic acid. Well, this time our acetate is going to be subtracted from, and our acetic acid is going to be added to by 0.01 moles of HCl. We're also assuming no volume change, so we'll just take those moles and subtract them from the molarities. So we can rewrite our equilibrium expression. We're going to have 1.8 times 10 to the minus fifth, which is the Ka, equal to X for the hydrogen ion concentration, times we had 0.1 molar initially of our acetate, and it's going to go down by the number of moles of strong acid that we added, so minus 0.01 on the top, over, we had 0.1 molar for our acetic acid concentration as well, but we're going to add the number of moles of strong acid that we added, so plus 0.01. So now this will become 1.8 times 10 to the negative fifth is equal to X times, we're going to have 0.09 on the top over 0.11 on the bottom. If we multiply both sides of the equation by 0.11, we're going to get 1.98 times 10 to the negative 6th is equal to 0.09x, and then we'll divide both sides by 0.09, and that'll give us x is equal to 2.2 times 10 to the negative 5th, and that is equal to our hydrogen ion concentration. So to get the pH, we'll take negative log of our hydrogen ion concentration. That'll be the negative log of 2.2 times 10 to the negative 5th, and that gives us a pH of about 4.66. So the pH of our buffer solution, after we added a little bit of strong acid, we added some HCl, became 4.66. Initially, it was 4.74. So the pH decreased only slightly. If we had added strong acid to a water solution, not a buffer solution, the pH would have fallen down to 1 or 2. But by adding it to the buffer, which was able to neutralize some of the strong acid, the pH only fell down by a few units. That's what buffer systems are made to do. They have a little bit of acid and conjugate base in there that can react with small amounts of additional acid or base to keep the pH essentially unchanged. Let's try another example. Calculate the pH of 1 liter of a buffer solution that is 0.25 molar in H2CO3, which is carbonic acid, and 0.5 molar in sodium bicarbonate. What is the change in the pH upon the addition of 0.002 moles of HNO3, which is nitric acid, so that's a strong acid, and a strong acid is essentially a source of hydrogen ion, and B, 0.004 moles of potassium hydroxide, which is a strong base, and any strong base is essentially a source of hydroxide ion. So we're going to have 3 parts. First, we're going to find the pH of just the pure buffer solution, and then we'll see how the pH will change when we add a little bit of strong acid, and how the pH will change when we add a little bit of strong base to that initial buffer. So our initial buffer is a combination of our weak acid, carbonic acid, and its conjugate base, which is bicarbonate ion. So we can initially write the dissociation of our weak acid, HC2CO3, and then we're going to have it dissociate into hydrogen ion, and we'll be left with its conjugate base, bicarbonate, HCO3 minus. Initially, we could set up an ice table if you would like to, and you would plug in your initial concentrations of your weak acid and the conjugate base. So we have 0.25 molar as the concentration of carbonic acid, 0 for our hydrogen ion, and then essentially this is a common ion problem because we have sodium bicarbonate, which the sodium is a spectator ion, but the bicarbonate is common to our dissociation expression of our weak acid. So we have 0.50 molar bicarbonate ion. Our carbonic acid is going to dissociate to some extent. We call that minus X. Our hydrogen ion will be formed and our bicarbonate ion will be formed by plus X. At equilibrium, we'll have 0.25 minus X for our weak acid, X for our hydrogen ion, and 0.50 plus X for our bicarbonate ion. We can write our equilibrium expression. We're going to have Ka equals H plus times HCO3 minus all over H2CO3. And we can look up the Ka for our weak acid, which would be H2CO3. The Ka for carbonic acid is 4.2 times 10 to the negative 7th. So once again, it's very small. We'll be able to make our simplifying assumptions. So when we plug that in, we're going to get 4.2 times 10 to the minus 7th is equal to X times 0.50 all over 0.25. because we're going to get to ignore this plus x and we're going to get to ignore that minus x. So that's why sometimes writing an ice table over and over again becomes redundant, because with so many weak acids and bases, you're going to end up getting to ignore the minus and plus x anyways. But go ahead and continue writing it if it's helpful for you. So we're going to want to solve for x because x is equal to our hydrogen ion concentration, and we're going to end up getting 0.50 times x is equal to 0.25 times the Ka, which gives us 1.05 times 10 to the negative 7th. And your x value should come out to being 2.10 times 10 to the negative 7th. That's equal to our hydrogen ion concentration. So next we'll calculate the pH by taking the negative log of that value. So negative log of 2.10 times 10 to the minus 7th gives us a pH of 6.677. So that's the initial pH of just our carbonic acid bicarbonate buffer system that we have made up. And I'm carrying it out to so many digits because we're only adding 0.002 moles and 0.004 moles. So the change is going to be fairly small when we add that acid or base to our buffer system. Next, we want to think about how our buffer system will react when we add 0.002 moles of our strong acid from nitric acid. So we're really adding H+. So if we rewrite our equation for the dissociation of our weak acid, we have H2CO3 breaking up into H+ plus HCO3 minus. And initially we have, some amounts of both of those in there. We had 0.25 molar of our carbonic acid, and we had 0.50 molar of our bicarbonate ion, and we're adding in 0.002 moles of H+, essentially. So we're dropping in hydrogen ion, and the hydrogen ion goes and it reacts with the base portion, which is the bicarbonate ion, and it's going to reduce the amount of base that's present at equilibrium because it reacts with some of that. So that's going to go down by the amount that we add the weak acid. And when hydrogen ion combines with bicarbonate ion, it's going to form more carbonic acid. So the carbonic acid will go up by the amount that we add the strong acid in by. So our equilibrium expression that we wrote on the previous slide, Ka equals H plus times bicarbonate ion over carbonic acid, CO3. We're going to see that adjust where this one's going to go down and this one's going to go up by 0.002 because that's the number of moles of H plus that we're adding in. So we really don't need to rewrite our entire ice table. Hydrogen ion will still be X. Bicarbonate was 0.5 molar, and that's going to go down by 0.002 moles. And our carbonic acid was 0.25 molar, and that's going to go up by 0.002 moles. We're essentially assuming we have no volume change from adding in these moles, so we can just add or subtract the number of moles to our molarity in this case. It's kind of a simplifying assumption as well. So this will reduce down to X times 0.5 minus 0.002, which is 0.498, over 0.25 plus 0.002, which is 0.252. So we can rearrange using the same Ka as before. So we're still dealing with the same weak acid. So Ka will still be 4.2 times 10 to the negative 7th throughout this. We can rearrange and find X, which is equal to our hydrogen ion concentration. And X comes out to being 2.13 times 10 to the negative 7th. Take the negative log of that value to get the pH, and the pH comes out to 6.673. So our original pH of just our buffer system that we found in part 1, we said was equal to 6.677. So comparing that now to the pH when we've added some strong acid, it's dropped down to 6.673. So it's slightly decreased, or in other words, gotten slightly more acidic by adding some strong acid to it. But it has not changed by very much at all, and that's due to that bicarbonate ion being to react away some of the additional acid. In the last part, we want to see how our buffer system will react by adding additional base. So we're going to add 0.004 moles of potassium hydroxide, which is really just a source of hydroxide ion. So if we rewrite our dissociation of our weak acid, we've got carbonic acid breaking up into hydrogen ion and bicarbonate anion. And this time we're going to drop in some hydroxide ion. And our hydroxide ion that we add in is going to go and remove a proton from our weak acid. So the base ends up reacting the weak acid carbonic acid away, so that goes down by the amount that we add our strong base by. And when the base rips a proton off of our weak acid, we form some of our conjugate base, which is bicarbonate. So that'll go up by that same amount. When we write our equilibrium expression, we're going to have Ka equal to H plus times HCO3 minus over H2CO3. But this time, we're going to have to add to the bicarbonate ion concentration, and we're going to have to subtract from the carbonic acid concentration. So we're going to still use the same Ka as before for our carbonic acid. We're going to have 4.2 times 10 to the negative 7th. We'll plug that in. X is still going to be for our hydrogen ion concentration, our carbonic acid concentration initially, and our carbonate ion concentration initially is going to come from the problems. We had 0.50 as our initial concentration of bicarbonate, and we're going to add 0.004 to that because that's how much base we're adding in. And our initial concentration of the carbonic acid was 0.25 molar, and we're going to subtract 0.004 because every drop of base that we add reacts with a mole essentially of the carbonic acid, forming another mole of the bicarbonate. So that reduces down to 4.2 times 10 to the negative 7th equals, we're going to have 0.504x on the top over 0.246. Rearrange and solve for x, which is your hydrogen ion concentration, and that gives you 2.05 times 10 to the negative 7th. And from there, you'll take the negative log of your hydrogen ion concentration, and that gives a pH of about 6.688. So compared to our initial pH of just our buffer solution, which was 6.677, you can see the pH has slightly increased from the addition of a strong base, but not by very much because it was neutralized by the weak acid in the buffer solution.